Okay, so let's take a look at AES. AES stands for Advanced Encryption Standard. And I'm not going to go through the history of AES, but there was sort of a contest to select a new version, a new encryption standard after the previous one. DES was decided to, it had some flaws in the design, a little bit of also limitations of the implementations as computers got faster. The ability to break the original design of DES became more and more realistic. So AES was designed to basically be a new algorithm that will be, secure for the foreseeable future. And so far, that's been the case. The general idea of AES, so I have two things here. One says encryption and one says decryption. And you'll see they run sort of forward or backward. So this is an example where it almost looks like a mirror, the encryption and decryption. AES always takes 16 bytes of input and always generates 16 bytes of output. So if we look at encryption first, we could call the output ciphertext and the input plain text. What does this mean? Well, we just learned that this means the block size of AES is 16 bytes. AES has one of three potential allowed key sizes. So you can have a 16-byte key, you can have a 24-byte key, or a 32-byte key. And again, because key sizes are given in bits, this is AES 128, AES 192, or AES 256. Regardless of key size, the block size is always the same. So the block size is always 16 bytes. It doesn't matter what the key size is. And the design of AES is on the left here. We see there's basically a number of functions that happen. So when we take the input data, we go through first add round key. We then go into SubBytes. We then go into shift rows, mix columns, add round key. And what you can see is there's kind of a little loop here. And each of these loops is called a round. So one round runs those same four algorithms. And the number of rounds depends on actually the key size. So the 16-byte, the default, what we might call it, AES 128, has 10 rounds in it. And the very final round is actually a tiny bit different. There's just one missing function for a slight efficiency gain here. And so there's actually 9 of the loops that are shown up here, and one that's shown down here for AES 128. What do each of those functions do? So really briefly, add round key. So the first function up here, what it does is it actually XORs in a byte. So up here you have the state, which is basically starts with the input data. So if this was my plain text, I might have hello world, let's see, how, and again, it's only 16 bytes. How are you? I was gonna say, so it's just whatever fit up to that. So that's my input data, and it gets XORed with part of the key. So obviously this input data, if this was ASCII, this would be stored as like the binary, and I don't know what these are going to be. These are just going to be me making up numbers that are kind of in the ASCII range, right? So we're going to have a bunch of data stored there. It gets XORed with part of the key. And so this key, again, is just going to be random looking binary data. And so we would take, say this is 22 and this is AB. We'd take 22, we'd XOR it with AB, and we'd write that output back here. So each input byte, each of the 16 input bytes get XORed with one byte of the key. The next stage, so again, after the key, we then go through SubBytes. SubBytes is literally a lookup table. So there's a lookup table that you can see the reference to, and it's a fixed lookup table. It has one-to-one mapping, so to guarantee you can reverse this, right? So if you know the input, you always get the same output, and if you know the output, you could get what the input was. So it's fully reversible. It's a 256 lookup table, so it's operating on 1 byte at a time. The next step just shifts some of the rows around, so all it's doing is permutating where our byte order is within the algorithm. And it's called shift rows because basically what you see is that each of the rows gets shifted a certain amount. So when we write out the state, we write it into this little square matrix. And you can see this row basically says it gets shifted once. This row gets shifted 2 spots. And this row gets shifted 3 spots over. So the new value of it is written over here. And you can basically see it also wrapped around. So this byte here, for example, is going to wrap around here. And you can see A10 is now in this location. A20, right, is going to wrap around to here. So you can see it's in this location. And A30 is going to wrap around to the next location. So shift rows is simply shifting the order of those bytes around. The next feature called mixed columns is actually performing some operations. So we won't get into details of how it's performing these operations, but it's performing the operations in such a way that basically the 4 bytes of inputs are mixed together to generate 4 bytes of output. So a single change in one of these bytes will affect all of the bytes of output. So what you can see is that as we run through multiple rounds of this algorithm, right, if we were to have a single change anywhere, if we had a single change in this byte, right, it's going to affect this entire row. The next time through, the rows get shifted around, so it's now going to start affecting other rows and stuff like that. So you can see how the algorithm ensures that if you have any change in the input, all of the other output bytes could be affected by it. Okay, so it's mixed columns. And then it will loop around back to, so after we have mixed columns, right, it's a new add round key, and then we loop back into this. As a small note on the round key, it's not actually the same key for every round. So there's a special round key, we call it, and this uses a key scheduler to generate a unique key per round. The round key is derived from the input key, so it doesn't add any security. But basically what this means is we have different round keys at each round. And yeah, so this is the basics of AES. The usage in base form would look like this. So you basically have 16 bytes of input, right? We have a key, and we generate 16 bytes of output. What this means is that if we had whatever the input is, right, it's going to go up here at the plaintext, run through the algorithm, and then generate our ciphertext. And so this is called electronic codebook mode, or ECB mode. And this is actually showing the decryption here. But in ECB mode, it basically means the same input is always going to map to the same output, because that algorithm I just showed you is deterministic. So if you have the same key, the same plaintext or ciphertext, it's always going to have the same output. So what we're going to look at next is how we might want to avoid that by using different what we call modes of AES to actually understand how this stuff gets used in real life.